We'll get started here. You have a pretty busy evening tonight, unfortunately, with all good stuff. Before we dive in, I just wanted to talk real quick about kind of how unique this is, that we're able to do this. One, that we've been chosen as the main stage this year by NASA, so that we're able to celebrate Pasadena in a big way. As you all know, you all live around here. Pasadena is a very unique place. We have a combination of design, technology, science, and innovation. It really is unparalleled elsewhere in the world. It provides a lot of great resources for you as creative, innovative people to get involved in different areas, and Space Apps hopefully is one of those areas for you. It's a place where you can get involved with people, with data, with ideas that you couldn't otherwise, but that just builds upon this foundation that's been created in Pasadena over literally generations, going back 120 years. And tonight is hopefully part of that, and we build on it, and we expose you to something here with the Carnegie Observatories that maybe you haven't known about before, didn't know was right here, kind of tucked into this little residential street. But hopefully then you can benefit and grow from this, just like everything else. So I would like to introduce John Mulcahy, the director of Carnegie Observatories, and he's going to tell us a bit about the past, present, and future of this great place.
Good evening and welcome to Carnegie. It's always good to tell people a little bit about us, because I know we're one of the best kept secrets here in Pasadena. On top of all the things that Joe mentioned, Pasadena is also the center of astronomy and astrophysics. You certainly are very familiar with JPL. We're going to hear more about that, and Caltech. And Carnegie is the other kind of angle that most people don't know about. But as I like to say, the universe was actually discovered here on this campus. It's important. I will argue the most important astronomy results of the last 100 years have happened here. So let me just quickly, I'm going to give a quick talk just to kind of tell you a little bit about what we do and where we've been. The Observatories was founded by George Ellery Hale, which is a name many of you in Pasadena will be familiar with. Hale was a solar astronomer at the University of Chicago in the early 1900s, and he convinced Andrew Carnegie to fund an astronomy department in Southern California and base it right here on our campus. And the reason for that was Hale was convinced that Southern California was the best place to do astronomy in the continental United States because of our great climate. And that, in fact, was true. Hale, for those of you, he did many other things. He was one of the founders of Caltech. He convinced Huntington to bring the Huntington Library here. The reason he was in Pasadena was to form the Carnegie Observatories. And as our first director, he really did some remarkable things. But I like to say that what he did was he actually built the 3 biggest telescopes in the world. Were built right here in Pasadena and designed here in Pasadena. Some of them you'll be familiar with. The Mount Wilson 60-inch was the first, the Mount Wilson 100-inch telescopes. And then eventually, with astronomers at Caltech, he built the Palomar 200-inch, which is down near Temecula. And these telescopes really defined all modern astrophysics, particularly the Mount Wilson 100-inch telescope, and this is a picture of Edwin Hubble, who was a staff astronomer here. He did all of his work here at Carnegie. And some of the major discoveries that happened in Mount Wilson, the 2 first ones were discoveries actually by Hubble. And I really argue these are the 2 most important astronomy results of the last 100 years, because they really redefined what our ideas of the universe. The first was that in Hubble's time, people thought the universe was much smaller than it really is. Most folks thought the universe really was composed of what we now know as the Milky Way galaxy. What Hubble showed was he showed this fuzzy thing that was called the Andromeda Nebula, was in fact a separate galaxy just like the Milky Way, just much further away than anybody had ever realized. He basically measured the distance to Andromeda and showed that it was so far away that it had to be a system like the Milky Way. It actually ends up being bigger than the Milky Way a little bit. I actually consider that the most important astronomy result of the last 100 years. And the reason why I argue that is because it completely changed our vision of the universe. It's very similar to when Copernicus showed that the sun was no longer at the center, or the sun was at the center of the solar system. That changed everybody's vision, right? Everybody thought the Earth was at the center of everything. Similarly, people thought the Milky Way was pretty much it, and there was an argument even where we were in the Milky Way. Some people thought we were in the middle of the Milky Way too. What Hubble showed was, in fact, we're in an ordinary galaxy. We're actually on the edge of that ordinary galaxy. And so it really changed our vision of the universe. And if that wasn't enough, about 4 or 5 years later, he showed that this universe was actually expanding. And of course, some people argue that's the biggest result of the last 100 years. And what's remarkable about that result is it implies, when you think about it, if it's expanding, that it expanded from something, and that something was the Big Bang, central part of the Big Bang. So this means the universe had a beginning. And so, of course, this was a very intriguing result. Later on, when you go to the library, you'll see pictures of Einstein. You spend a lot of time here at Carnegie trying to understand this result. So these two results really launched the field of cosmology, which is the study of the universe from its beginning to how it changes in time. That really happened right here on this campus. As if that wasn't enough, our understanding of how stars are and how they evolve and how they change in time also happened here at Carnegie using the Mount Wilson telescopes. And I put active galaxies. This is a field we don't talk a lot about to the general public, but most galaxies, that I'll show later on, have giant supermassive black holes at the center and releasing huge amounts of energy. You've heard of quasars. And those active galaxies were, for the first time, found here by a man named Seifert, who worked up on Mount Wilson. So this was a great place for an observatory at the turn of the last century, and these great telescopes did a lot for us. The problem was Los Angeles grew, and so this is a good example. I think I'm going to keep loads on here. These are 3 great pictures taken from Mount Wilson. 1910, 1920, even by 1925, you can see there was some light pollution. And now you go up there, and it's just like, it's brighter than having the full moon up. And so this really makes it impossible to do deep sky astronomy, which is what we do here at Carnegie, from Mount Wilson. And so for this reason, Carnegie moved our operations, our telescope operations, to southern hemisphere in the 1960s. We started that effort. And to a place called Las Campanas. This is our observatory. This is a picture of it in Chile. Chile is a great country for astronomy for many reasons. This particular location is extremely dry, as I'll show in a minute, and it has a climate very similar to California. And so it turns out it's actually better than California. It's even drier. Our typical observatory gets about 1 inch of rain a year, which in Southern California, I think typically we get maybe 13 or 14. So it's drier even than it is during drought years. Just to remind you where Chile is, it's down here. I think most people know. We're about 500 miles north of Santiago. That's the nearest city. But these are some pictures of it. And the remarkable thing from the pictures is just how dry it is. There is no green on our mountain. I mean, that's what an inch of rain or less a year will do for you. I mean, it is really, we're at the edge of the driest place on the earth. Despite that, you actually see a lot of wildlife, which is really always surprising to me. That's a guanaco. It's a relative related to a llama. You see a lot of them. I was there just last month and saw 9 of them on the mountain, so they hang out quite a bit. The observatory is very remote. It takes us 24 hours from the time I leave my house to the time I get to the top of the mountain. And so this means when we go, we stay for a while. I usually stay for about a week, collect data for a week, and then bring it back, and then we work here in our offices in Pasadena. I was saying earlier today that I spend most of my time staring at a computer, which probably most people in this room probably do. But what we do is about 3 or 4 times a year we go to Chile, collect that data, and the rest of the time we're in our offices here in Pasadena working on the data. And so why do we go all the way to Pasadena? It seems like a long ways to go to Chile. And the reason is, for a spectacular image like this, this one I may change the lights for a second, just to show you if you can see it. The sky is exceptionally, there it goes. The sky is exceptionally dark in Chile. We are so far away from any city lights. The problems we have at Mount Wilson are not going to be a problem in Chile for many years to come. But the other advantage of Chile is it's in the southern hemisphere. And it turns out the southern sky is actually in many ways more interesting than the northern sky. For one, the Milky Way, which is this thing that runs across there, goes right overhead in Chile. It's actually the center of the Milky Way galaxy is actually located in the southern hemisphere. But the other thing is that the Milky Way has 2 companion galaxies, the Large and Small Magellan Cloud, which are extremely far south. You can only see them very far in the southern hemisphere. And these have very different sorts of stars than we see in the Milky Way. So it turns out a lot of these stars are less polluted in the sense that they are earlier generations of stars than we see in the Milky Way. And so they make very unique things to study, which we don't see anywhere else. Go back to that. Let's do that. So at Carnegie, we started with 2 small telescopes, relatively small telescopes, 40-inch telescope, 100-inch telescope. These are still used every single night of the year. But our main facilities are these much bigger telescopes. If you haven't seen a modern telescope, they're quite different in design. We have 2 twin telescopes. They're called the Magellans. They're 6.5 meters, or about 21 feet across. So that's the back of the mirror there. So I mean, these telescopes really allow us to kind of peer into the universe in ways that you just could never do anywhere else. And the other great thing about Magellan is that the system has what's called adaptive optics. That is, we can correct for the atmosphere. And the atmosphere tends to blur things, which is why things like the Hubble Space Telescope, you go into space to get above the atmosphere. We can almost make up for that entirely now on the ground by correcting with adaptive optics. I don't know how well this comes from your angle, I can't see it. This is what it looks like. This is a star system looks like without the adaptive optics, and this is what it looks like when you correct for that atmosphere. So if you're trying to interpret this, and it looks like this is what it really looks like, and this is what you see, it's pretty tough. This system actually delivers better image quality than the Hubble Space Telescope. It delivers the best image quality of any optical telescope in the world. So I thought I would just briefly mention like 3 topics that we work on a lot here, just because I always want to talk about some astronomy beside our telescopes. The first is one of the big things that the field that started with Hubble, which is how did the universe get to what we see today? This is one of my favorite images from the Hubble Space Telescope. This is the ultra deep field, it's called. This is a deep exposure, a couple week exposure with the Hubble staring at a very tiny patch of sky. And everything you see here pretty much, except for like 2 or 3 objects, is a galaxy, a distant galaxy. Most of them about 10 billion light years away on average, 8 to 10. And the remarkable thing about this image is how diverse the galaxies are. You see different colors, that tells you that it's different sorts of stars. Systems that are red are old stars, systems with the blue are new stars. But you also see different shapes. You see things that look kind of like a spiral galaxy, like our Milky Way, and then you see other things that look kind of roundish. And so one of the main things we work on, including myself here at Carnegie, is how did the universe go from a Big Bang to create this diversity? And it's a question we really are trying to understand. Here at Carnegie recently, we've had some great discoveries of some very, very old galaxies. We're almost seeing the very, very first galaxies in the universe now. These little blips, you can barely see them, these are the close-ups of them, are two objects that were discovered with the Magellan telescopes using an infrared camera called Fourth Star there. These galaxies formed about a billion years after the Big Bang. That's pretty old. It makes them almost 13 billion years old. But the remarkable thing is they're red. And red means that these are systems that are not forming stars. They've shut down forming stars. So what happened in these cases, these galaxies formed, and then almost instantaneously stopped forming stars. Well, why is that weird? It's weird because the early universe had a lot of gas and dust, and so that's the place where you expect a lot of stars to form. And so in fact, our own Milky Way galaxy is 10 billion years old. It's still forming stars. So why did these guys stop forming stars almost immediately? We don't really know the answer. But this is one of the things we're trying to understand. Why are there galaxies like this? Why do some galaxies die kind of almost instantaneously while others like the Milky Way continue to live? Black holes are always very popular. I like to work on black holes, so I talk about this a lot. On the right here is that same image I showed a minute ago of the Hubble Ultra Deep Field. So in that image, what you're seeing light from the stars. On the left here is the same exact image taken with an X-ray telescope, the Chandra X-ray telescope. It's kind of the X-ray version of the Hubble Space Telescope. And what you're seeing here are X-ray sources. And these X-ray sources are actually black holes in these galaxies that are accreting. As material falls on towards the black hole, it heats up and emits huge amounts of X-rays. So it turns out when you take an image with the X-ray telescope of the sky, almost everything you see is in fact a black hole, an accreting black hole. To give you an idea how these are big black holes. These are 1 million to 1 billion times the mass of the sun. There's different kinds of black holes. These are what we call supermassive black holes. And so what an image like this tells you is that most galaxies in the universe, including our own Milky Way, have these black holes at the centers. So recently, a couple years, now it's been a couple years, but I was studying X-ray. I'm actually half an X-ray astronomer, so I put this topic in. I found this particularly interesting thing. This is an X-ray source. It doesn't look very pretty, of 2 X-ray sources very close to each other. And so I had the question, well, are these things related to each other? Are they 2 black holes that are somehow about to merge? And you can't really tell from the X-ray data, because it could be one of the black holes is close and one more distant. But then I went to the telescope and took an optical image, and this is what you see. Once again, it's not the prettiest image, but it's actually pretty spectacular. This is very far away. And what you see here is actually 2 galaxies. And these are what we call tails. These tails are a sure sign of systems that are interacting. This is how galaxies interact. And so if you then go back and plot, now the blue is the X-ray on top of the optical, you can see these X-ray sources align with those 2 galaxies. So this told me right away that we had found 2 black holes in 2 galaxies that are going to merge. So I went down the hall, and I have and I had a guy who was a postdoc who was doing simulations. This is a complete simulation of the system. So what he's done is he's just taken the laws of physics and thrown it in the computer. And you see, this is the first galaxy went by the first time. This is time in billions of years. Astronomy, that's how you have to count this. And after about 2 billion years, that other galaxy, see the galaxy kind of recovered from the first encounter. He comes back. This time he's not going to escape. This time gravity got him. And what you see there is an image with 2 galaxies with 2, and you see my image. It's actually a pretty good simulation. It matches the data pretty well. The interesting thing is that the simulation you can of course keep running. With my data I can't do that because I have to wait 2 billions of years. But there you go, and you see that these two galaxies are going to merge. And this is what they will, they probably already look like. It just will take us a few billion years to see that light. But eventually what this means is these 2 galaxies and their black holes are going to merge. So when the galaxies merge, they're going to form a single galaxy. But the thing you don't see in the simulation, but it is there, the black holes are going to merge and form a single black hole. And so this is, in fact, this was the first discovery of what we call a binary quasar, because this is 2 black holes emitting a lot of energy. And this is an example of what when these things merge, they're going to emit gravitational waves, which you've heard a lot about in the last month from Caltech and various folks. Let's see. So I'm doing pretty good here on time. So the other great thing about telescopes is sometimes there's complete mysteries. This is one of the great things about astronomy. You could be working on something you have no idea what it is. And this is an example of another phenomenon that's been in the news a lot, which is what I talked about, called fast radio bursts. These were found a few years ago. People were looking through old radio data, and they saw these instant bursts of energy. These last less than a millisecond. It's a very short time period. And so the question is, what were these radio bursts? What are these? They were nicknamed fast radio bursts because they are bursts of energy and they go by fast. But they were found in old data. And so the question is, we couldn't follow up to figure out what they were. And there were questions. Some people thought they were fake problems with the telescope. Some thought they were something on Earth. But the obvious suggestion is that these were related to exploding objects like supernovas. And then in 2014, we got really lucky. We actually caught one in real time. This is the radio data. We were monitoring this from Australia, and there all of a sudden we found the fast radio bursts. So I quickly got to my Magellan telescope in Chile, where I happened to be at the time actually, which made it easier, and looked at it and saw nothing. And so this is surprising. So the answer is, well, yes, it's surprising if you expected these things to be related to supernovas. This is the most complicated plot I'll show, but this is brightness versus time. And when a supernova, this is an exploding star, goes off, it actually gets brighter in time. This shows it. This shows the path over a time period of weeks, and the supernova get brighter. And here's a different kind of supernova. These are 3 different types, and they always get brighter. This was the limit we found, so this was the upper limit. Our object, our non-detection, meant it was less bright than that, which could rule out this type of supernova right away. Then we took another observation a couple weeks later, and that could rule out these 2 types. So the lack of seeing something actually told us that whatever these fast radio bursts are, they're not related to supernova. And that was pretty surprising. Should never put out a press release that says we found mysterious radio signals and we have no idea what it is. It ended up in the UK tabloids, and it has been interpreted as aliens. And so unfortunately, it's probably not aliens. We still don't really fully know what this is. But this is one of the exciting things. This field didn't even exist 5 years ago, and now it's a whole new field in astronomy. So I'm running out of time. I've actually gone over time, but I'm going to very quickly tell you, this is why you always have to build the next biggest telescope. This is the telescope we're building next in Chile. It's called the Giant Magellan Telescope. It's 7 mirrors that work together as one mirror. Each mirror is 8.4 meters, or about 25 feet across. Yeah, it's giant. That's why it's called the Giant Magellan Telescope. This telescope has basically 100 times the collecting area of the Hubble Space Telescope. That means it collects light at 100 times the rate, go much fainter. Here's a little example. It's sensitive enough that if you had this telescope in the ground, you could see a candle on the moon. Pretty good. The telescope will have about 10 times the resolution of the Hubble Space Telescope. That's the ability to see detail, which is important for lots of things. And in this case, with this telescope observing from Los Angeles, you could resolve the structure on a dime at the distance of Las Vegas. It's pretty impressive. This shows you why you build big telescopes. This telescope is well along its way. We actually have 4 mirrors. These are the 4 mirrors that are already being built. We just started last year the middle mirror. That's why it has the hole in it. Total of 7. This is kind of where we're at on the time scale. I didn't show you, but we have the site ready to go. It's going to our site in Chile. We actually formally began construction last year in November. We had a big ceremony in Chile. We started pouring cement, which is very exciting. And first flight we're hoping in 2022. So this will be the future big telescope. And I should point out this telescope is being built here in Pasadena. It started on our campus, but now they have a whole separate facility that's near Sierra Madre, I think. Right? Yes. And so this is just one example of how Pasadena will remain kind of on the forefront of astronomy. And I just thought I would end by saying, if you want to follow more about Carnegie, we have open houses, we do various public lectures and things. You should follow us on various social medias. Thank you. And we're going to give you tours later. So you get to, if you have questions, you'll have a chance.
Yes, the tour, it's awesome. What these guys do here, it's like full stealth mode, but they're literally discovering the universe, you know. As well, I mean, you can point around Pasadena and be like, they're discovering the universe, they're discovering the universe. It's awesome. So, and this is one, though, that I don't think many of us have had a chance to see before, so hopefully you really enjoy that and appreciate the offer to include us here. Up next, going from strength to strength here, we have Tom Soderstrom, who is the Chief Technology and Innovation Officer for JPL. And he's been a big supporter of Space Apps from the beginning, but definitely since we came and started here last year with this. So please welcome Tom.
We'll see if this works.
Yeah.
So prove that the world runs on PowerPoint. Usually I like Prezi and PowerPoint, but just kind of mix it up. Just curious, how many of you are programmers? Wow! All right, that's cool. How many are designers on the front end? Okay. How many are card-carrying data scientists?
I don't have a card yet.
How many would like to be a data scientist? All right, good. Who is an Internet of Things strategist? So Gabriel and I work together. Gabriel, you want to say hi? We do a lot of, I'm going to talk about what we do at JPL, but how does it apply to what you do? Well, it has everything to do with what you do. We do prototypes and we do rapid experimentation, and the things that make it continue, the things that don't, we drop like a hot potato. So I'm going to show a little bit. This is JPL. Who's ever been to JPL? Oh, wow. So yes, at one point in time we had water. So what we want you to do is help us dare mighty things. And here's what's coming up in the next few years. We're going to go to Europa. Very good. An icy planet. Why did we go to Europa?
More water there.
There's water, thick ice shelf, thick crust of ice. And what's inside that is water. And we know there's energy there because we see geysers come up. So energy and water equals life, perhaps. So that's going to be really interesting. So we're really interested in icy planets. And that's funded and it's coming. We're also going to do what?
Asteroid capture?
Yes. We're going to capture an asteroid or a rock from an asteroid and put it in orbit around. You guys are good. And why do we do that? Well, one day, we hope, it never happens, but if a really big asteroid comes close to us, we want to be able to understand it enough to redirect it. We know how to do it. You just put equal and opposite force. Put something way out early and it'll pull off course. But we have to detect it really, really early. How are we going to detect it? There's lots and lots of data to crawl through. Citizen science, hackathons. All of that could help us see it early and avoid it. One day, we're going to send more people than Matt Damon to Mars. Because we always have to rescue him.
No matter what.
We could actually send people to Mars today. It takes about 10 months. We just can't get them back. So to get them back, we have to come up with new technologies. Propulsion. Propulsion is a really big deal. So solar electric propulsion is what we need to do to get humans to Mars, and that's what this mission, the asteroid mission, will conduct. So it's a technology demonstration as well. The other thing is cloud computing. Anybody not using the cloud today? Nobody raises their hand. Of course not, because you're starting with the cloud. For us, it's been a big transition. We've been doing cloud computing for 8 years now. These are two instruments you'll soon hear more about. So what we do at JPL and NASA is we have deep space things. We look for Earth 2.0. It'd be a nice thing to find it. One day we'll need it. We look for how the universe started, where it's going. We look for life elsewhere. We also send out spacecraft to look back at Earth and try to help predict tsunamis, floods, droughts, etc. Both of these are radar instruments that are going to look for water. What's interesting about these two is those two are doing 80 times more data than all of the other ones combined that we've done. So all of a sudden, the idea of, since you're all programmers, I'm a little geeky, the idea of sending, what we used to do is to send the data to the processing and process the heck out of it. Can't do that anymore. We have to send the processing to the data. So what does that spell? Cloud computing. And we don't have data centers big enough for this. So all of a sudden, the whole paradigm changes. It goes to micro services. It goes to creating reliable systems out of unreliable components. Who's going to do that? The next generation is who's going to do that. So we are working a lot with innovating companies to figure out how to do this. It's not easy, but we're getting there. So all new missions actually start in the cloud for us. Now I'm going to talk about the Internet of Things strategist that you will all become. Internet of Things is really powerful. Today's toy is sometimes just a toy, but often it's tomorrow's tool. So today's toy being tomorrow's tool. Cloud computing was what we backed up our data into using 8 years ago. Now it's table stakes. So the user interfaces are changing. So how you interact with computing is changing. Then we convert it and change it in the cloud, and then we act on it. So the Internet of Things is a really big deal. I want to play just one small video here. If I can figure out how to do that. No sound. No sound.
We'll see. We don't know. We'll find out.
Oh, here's one. Let's see if this works. Just want to show you why we care about something like Internet of Things.
JPL Info.
Oops, wrong.
Welcome to JPL Info. You can ask.
Let's do. Whoops, wrong. All right, forget that one. What you see here is actually lights. So this is a screenshot of cybersecurity. So every time that somebody attacks us, we count it, and if it goes to the danger zone, it gets yellow. If it's really bad, it gets red. And lights turn off on all of JPL, so people see it immediately. We also listen to the firewall. You can hear it play piano for you. So if you're not paying attention, all of a sudden, something's happening, and you can pay attention. We can speak to the computers. You can ask all kinds of questions about JPL. So all of these Internet of Things, we're also sending data into Watson, our data into Watson. It crunches on it, and it speaks it back. So all of these things are brand new for us. And by the time you guys start playing with this in the hackathon, for instance, the NASA Space Apps Challenge, be creative. Try these Internet of Things. Use Arduino's, Raspberry Pis, 3D printing. All of these things are what's making our missions possible. This is Gabriel, very serious scientist here. And we're using 3D touchscreens and 3D models and 3D printing with very expensive 3D glasses. But it works. This is what it looks like in a clean room. And one of the additions here is this big touchscreen with a video conference and the ability to take your smartphone over into the spacecraft. This is a spacecraft called SMAP. And see the picture here and video conference it out. All in, this whole thing was like $10,000, and $5,000 of that was the stamp. So all of a sudden, things are possible to do quickly. And it was a prototype that changed completely how we do missions from now on. We do lots of hackathons. We do anything from the fancy, higher-end hackathons to the scruffy, fast hackathons. I'm not sure what the NASA Space Apps Challenge will look like. We do them outside. We do them inside. And we know what drives you. So do help us to take the next leap for humanity. This is what this is all about. It's about getting you all involved in changing our future for the better. So we want to thank you for participating in NASA Space Apps Challenge. And if you want to look at the challenges, there are, you just search for NASA Space Apps Challenge 2016 and realize that all of those challenges are hooked into real NASA data. So it's about the open data, it's about crowdsourcing, it's about citizen science, and it's about Internet of Things to enable it. So we thank you very much for being here and helping us help humanity.
Thank you.
Anybody have any questions?
Are you guys so awesome?
That's a great question. Anybody want to repeat that? It's, in the end, it's about having fun. It's about creating energy, and it's about, no recording here. It's about breaking rules. It's about challenging and breaking and speeding things up. Agile development is now table stakes. It used to be a big deal. So it's about thinking like a startup. JPL is an 80-year-old startup. It's all kinds of innovations happening all the time, and it's a fun place to be. So we get to work with very, very bright people. It's like herding cats sometimes, but there is. Yeah. Any other questions?
Well, actually I do, but I don't know if I should ask now. There was a lot of questions about participating. Are you okay to have a spectator to to go observe how the game goes? And I mean,
I'm sorry, observe what? I'm sorry.
Spectator.
For
Space
hackathon?
Apps itself?
Yeah, for next week.
Yeah, just talk to me after.
Yeah, that's what I was saying.
Yeah,
Okay,
yeah.
yeah. So.
I would highly recommend, if you've never been to a hackathon, it's really fun. To me,
Mhm.
this is probably pretty unpopular, it's a rave party without the drugs. It's exciting, it's where you go to socialize and have fun.
Actually, I just registered 2 days ago, but I want to say thank you that you are welcoming all type of level from the beginner, intermediate, into advanced. So I'm glad you do that because you don't know who you are.
The other amazing things for hackathons is everybody self-organizes. There isn't, Joe is not going to say, okay, you go in this team, you go in this team. It's self-organizing. I think it's very impressive, and it works. Somehow it works.
Yeah.
Mhm.
Give people credit.
Thank you very much.
Thank you.
And I'd like to say GMT is awesome.
Okay, so that's two incredible examples of what you can do with technology and innovation, and we've seen kind of the results. Now we're going to meet a few of our sponsors who are going to give you guys the tools and the information and the assist to help you do it yourself, or at least get on the path wherever you may be along the way. So first up is Ajay Mugara from Intel, who's going to talk to you about all sorts of It's hard to match that.
Tough act to follow.
It's a very, very tough act.
All right. Thank you so much. And I'm from Intel, Ajay Mugara, and we will be sponsoring a few boards, and we'll talk about some of the hardware that we sponsor and things like that, right? So I'm here to kind of talk about the technology inspiration, right? Talk about not how people are trying to take this Internet of Things and what are they doing with it, right? I am the product manager of Internet of Things at Intel. So I look at how Internet of Things can be applied on a large scale, right, on industries, and how it can be applied to different parts of the world. So I'm Ajay, as I said, this is a support team that will be here during the Space Apps Challenge. So Grace will be here, and Justin, so just so that you know where to look for in case you need some help using the Intel products. So I will talk about a few things, right? So one of the big things with the compute evolution, as what we are calling that at Intel, right? So you are seeing that over time, we had this dumb terminals, PCs, laptops, smartphones, and tablets, and things, right? All of the things combined so far, right? By 2020, you're going to see them at 10 billion. But what will happen with Internet of Things is the ranges range from 40 to 50 billion. So you're going to see 40 to 50 billion devices that's going to get online. And why is that happening? It's happening because of a couple of things, right? It's happening because the cost of sensors in the past 10 years has gone down, it's gone down significantly. Cost of the bandwidth in the past 10 years has gone down 40x, right? So the bandwidth costs are so important. Like in the past, when we talk about things that are connected or not connected, today you have 85% of the things are not connected, right? From smart things, if you call it. They're not connected. There is some kind of software or embedded software that's running in it, but it's not connected. But imagine if all of those devices are connected, and the only reason they can be connected is because the bandwidth costs have gone down. And the cost of processing as well has gone down 60 times down, right? It's the cost of processing has gone down so much that you're able to take a lot of these data and make wonderful things out of it. And what can you actually do is, this slide I really like, because just imagine that you could deliver 1% improvement, just 1%, right? 1% improvement in any of these things. In aviation, if you save 1% fuel saving, it's going to reduce. We're going to save $30 billion. So it is just 1%, right? And 1% of everything you try to do it with technology and innovation, it can save trillions of dollars, right? So like you were actually wondering, like, hey, look, there is a space app challenge, and I want to do these app challenges, and why is he talking about this 1% and things, right? And what we have seen is the innovation that comes out of many of these hackathons and events largely fuel the next generation of that innovation. Right? And we have seen that with PCs, we have seen that with servers, we have seen that with cloud, we have seen that with data, and Internet of Things is not new. And I have seen that evolution. I've been with Intel for 18 years, and I've worked on a lot of these different platforms, including automation with cars, automation in industry, in oil and gas segments, a lot of these segments, and this is real, and now I do Internet of Things. And I was just talking to some, the last year's winners of Space Challenge. They were talking about a project they did, which was automating a plant system, okay? So that you can just find out the ambient light, the moisture sensor, so it's a plant, so it automatically waters the plant, everything, right? So it's a simple project. You can go to any, like Instructables or something, you can replicate that project. But somebody came in and they added a twist to that innovation that I never expected. What they did was they took that entire plant system and they connected to a Fitbit API. So if you don't meet your fitness goals, the plant is going to die. Because it's not going to get enough water. Right? So the pitch for them was, you can see the reflection of your health in the life of the plant. I was like, wow, right? And think of any ideas. Like I go to these events all the time to see these type of innovation. And like these guys came up with this project where they said, look, we are very lousy dancers, and I'm one of them. Right? They said, if most people dance for music, they said, let's reverse the thing and let's dance and we'll generate the music based on moves. And they did it. And they did it very successfully, right? And every time I come up with a project and I think that, okay, that's the innovation and this is what I think people will use, and I find some use for it. One of the classic examples is we're working with the city of Los Angeles to conserve water for California drought problem, right? And we came up with this project where it says that you can calculate the vibration of water that goes through a pipe, and it will just measure like how much water consumption you're doing. So it's just a vibration sensor that sits on a pipe, and we could just calculate saying how much you use. So if you take long showers, it will come out in a graph and says that you take long showers, so take less. That's what we expected people to use that project for, right? We put the code out there, and I was shocked. This one guy, he came up and said, "Thank you for your project. I did something very cool." I said, "What did you do with it?" He took that project, and he happens to be a high school music teacher, and he teaches students how to play flute. And he said, "I'm going to use your project, so I teach students how to blow through the pipe in the right way, so that first notes of music comes out like that." So he graphed it, and he said, I was expecting people to use it for water conservation, you use it to teach music. Who knew, right? So I had few examples, like I'll just not go through all of this. And people did this air guitar, which is a beautiful project. They used, like all of this, the common theme is they use Intel Edison. And essentially you have the little gloves, and it's got like certain sensors. You can touch it, and you can feel it, and it actually plays. And it was awesome. The guys, the way they demonstrated this project, they did everything without a guitar, with just a little bit of a technology, you can actually play music. So these were few projects. I like this project as well. That was a constant danger project. So these guys had a bunch of sensors in this little box where it kind of shows you the meter of danger that you're in. It had lots of data. So it says like, hey, look, there is something going on. The pollution is bad, whatever, right? So a lot of different projects. I'll just not go through it. And all of this is made possible with Intel Edison. We are I'm happy to announce that at the NASA Space App Challenge, we are going to be distributing 60 of these Edison boards, so that you could use that. And after the event, I'll have some of these, so you can take a look at it. It's a very tiny module, and it's got Wi-Fi, Bluetooth, everything in it. And there's an Edison module, and it can fit it on site like an Arduino board. I can show you, right? Yeah. So this is actually the module, and this is the Edison board that you can connect to an Arduino breakout board. So you can connect any Arduino sensors, right? So that way you're able to do it. So that's what this product is. And it's got if you look at the Arduino breakout board, it's got a bunch of digital input output. It's got PWM outputs, analog inputs. So now if I just give you the board, you can't do much with it. So I'm actually giving you, we're also giving 60 of this sensor kits here, so that you could, it has these following sensors, right? A buzzer, a button, LED, sound, a rotary angle sensor, touch sensor. You would just imagine, right? Like these sensors, and you can do amazing things with this, right? People who come to my events sometimes, and there's one guy who came to the event really upset, and I said, "What's wrong with you?" And he said, "Look, I bought a brand new Audi, and somebody came and kicked my car. So I want to build a technology with vibration sensors. With just this, he used a sensor thing, and he had this camera that he connected. And he said, anybody touches my car, it takes a 360-degree pictures all around it and texts it." He came with a purpose, and he right? So all these people come to these events, and it's amazing to see what you can do with this. Just a standard set of these 12 sensors. Right? These are all little projects, and connecting all these loose wires and sensors, we enable you to take those products to production as well. You can miniaturize it, and you can do a lot of different things. I'm the guy behind the scenes of America's Greatest Makers TV show, where we sponsored, it's by Mark Burnett, one of the Shark Tank things, where we've seen some amazing things of technology and what people can do. I'll give you another example, a favorite example is there's this guy came to this event we were in, and he said, "Look, I live in Minneapolis," and this event was in Boston. I said, "Okay," he flew all the way in from Minneapolis. He said, "It's too cold." I said, "Yeah, I know. It's cold. That's why we don't do events there in winter." And he said, "Look, it's very painful for him to walk his dog." I said, "Okay, so what?" Then he said he wanted to use this technology to tie it to the dog's leg, and when it does its business, right? So he wanted to use a Bluetooth so that it actually gives an incentive box on a tree or something, and it throws a bone or whatever. So he wanted to potty train the dog. And he actually successfully demonstrated, that you can actually do it. So using IoT technology, who knew, right? So here is we also provide you with a set of software components, which is this Edison board. runs on Linux. So it has got like, you could use JavaScript, C, C++, Python, or any of these programming languages to be able to program these boards, right? We made it as simple as you can get. What we have done is we also put in like about, there's many code samples on the website. So these code samples are simple things from smart alarm clocks to an earthquake detector to a bunch of other projects that you can actually use as a starting point to be able to take these things and use that as a starting point to innovate on top, right? Because as I gave you the water plant example, somebody took this project, replicated the entire thing in 2 hours, and they were able to add innovation on top. That's what we would like to see happen, right? Well, this is just an architecture in terms of all of this. I'm not going to the details of any of these things. And here is where you can go, the Intel Developer Zone, which is software.intel.com/IoT. You can go there to find a lot of information on the thing. And in fact, there is the website here, Intel and Microsoft work better together. So that's because they had the big conference, and we made sure that there was a lot of code examples on how to connect to Azure Cloud. And because at the end of the day, you want to be taking all of this data to the cloud, you want to be able to add innovation in the cloud. And do different things, right? Because one guy built a smart alarm clock, and the alarm clock has not changed for a long time. But his innovation was he took like the data into the cloud. So if you know that your meeting is cancelled or your flight is delayed, it can wake you up 15 minutes late. Or if there's a traffic accident in the meeting that you want to go to, and it knows where you want to go, so it will wake you up early so that it tells you that better get on your road because you're going to miss your meeting. So all of these things are very possible today, and with the technology that exists, and we have shown that through examples and codes, and with using this hardware and a combination of sensors, we'll be able to do all of that. So we also, one thing that we ask in return is, with all the hardware that we sponsor and everything else, is that if you do any of your projects and you post your project on Instructables, so others can benefit. Others can use that as a starting point of innovation. Because a lot of the libraries and everything that we built is completely open source. We have opened up everything, and all of the code is out there. So that way, like any time that you're doing these type of innovations, unless you have an idea of taking it to a startup and want to do that, that's also fine, right? It's not like you have to post everything here. That's not the expectation. But if you do, then others will benefit as a community. And then, like just again, as I said, right, how explore, innovate, and create the new world. And with IoT, the pace of innovation that I've seen out of all of the other efforts that I've worked on in the Intel over the past years, the pace has gone up 10x. The pace of innovation that I'm seeing with all of these different things being able to connect, and how when you start getting the things talking to each other, the amazing thing is that I think we're going to start seeing that next generation of innovation come through IoT. I'm very happy to be part of it. I'm very excited to be a sponsor for this event, and I'm super looking forward to see what innovations you guys are going to come up with. Thank you very much.
Real quick before you step down, I wanted to just clarify, so to get access to these boards, what does the team do? Do you want me to answer?
Oh yeah, go ahead.
You want me to? Okay. So if your project, if your idea for your solution will put these boards to use, then there will be a way, we'll post information this week, there will be a way to contact Intel, let them know, and then basically to sign up to get boards. Okay? They're not going to be handed out at the door. Okay, so, but if your idea is going to use them, and please dig in and look, they are easy to use to get up and running. So if you weren't thinking about using one, look into it, come up with ideas to use them, even if it's your first time, that's totally fine. But then it'll just be kind of a request system to get them. But hopefully we'll have enough for every team that wants to use them.
Correct. I think we are doing about 60, right? So the first come first served basis. So we are sponsoring 60. So that's about how much we have seen in the past events. So based on that calculation, that's how much we have allocated. So I mean, this has got like both the board and the kit, right? It's a request for it. We'll be happy to say, right?
Yep.
Do you guys have the smaller boards? smaller boards for Edison, not the Arduino ones?
We do have the smaller boards, but the thing is, usually what happens with the smaller boards, I have one right here. With the smaller boards, what happens is connecting any of the sensors is very hard. So to connect to any of the sensors, you need to use a soldering iron, and you need to do a lot of this fancy stuff to be able to do this. When you're ready to productize it, it makes more sense to use the smaller boards, because in most events locations, you try to use a soldering iron and fire hazards and all of that things. So we've been specifically asked not to force that along to the, because most developers are not, they're not going to use that kind of stuff. Right? I mean, in fact, I have this, and I have like we have a lot of things, right? Like for example, this is like a Curie module, which is like size of a shirt button, and it has got enough processing power for you to make anything smart, right? So, and which is like literally a size of a button. But in order to use these kind of boards in hackathon type settings, you need to know how to use them, and you need to have a lot of technology behind them. So that's why we sponsor these ones, which are easier to connect any of your sensors and start your prototype, and you'll be able to prove your concept for real. And once you have that concept in place, and once you want to really productize it, then obviously you have multiple choices. Any other questions? Are you guys excited about the event?
Yeah. Good.
So next up, we're going to have Brett Statham from Microsoft. He spoke at the first meetup that we had, and he has some additional info for you now. So Brett.
All right, good evening. How's everybody doing?
Good.
Fantastic. As Joe said, my name is Brett. I'm a technical evangelist with Microsoft based here in San Diego. Who was at the first meetup? Okay, cool. So thankfully, Daniel made it back safely from Mars. He's here now in the back of the room. So, anyhow, so tonight what I wanted to go over was just a little more concrete examples of sort of how we think our technologies might help you out in some of the different challenges. First of all, if you weren't here last week, we have a website with links off to training resources on a number of different Azure Microsoft Cloud Platform technologies out there at ak.ms/space apps. And I'll give you that URL here at the end as well. And then also, when we're done here, I'll post the slides, and those will be available on that link as well. But if you were to jump up to the 2016 SpaceAppsChallenge.org website, see that there's really sort of 6 different categories of challenges in there. So we've got technology, aeronautics, space station, solar system, Earth, and journey to Mars. And so what I did is I kind of put myself in the mindset of a hacker, and I said, well, if I'm going to join in and take part in one of these challenges, how could I use Microsoft technologies in the different sub-challenges that popped up? And so in the technology one, there were a number of sub-challenges within there, and I kind of came up with ideas for each. I'm not going to read through each one of these. But I thought this one was kind of interesting. Backfill my model. This is a challenge where basically the idea is that you might have some idea of the outer projection of a 3D printed surface, but you don't necessarily know what the inside structure of that needs to be in order for it to be a solid, viable, printable device or object. And so in that case, I need a way to sort of say, let's take that sort of outer interface of the thing I need to print and have something generate that internal surface for me. And maybe I would be using this for generating large structures, and so I might need a lot of computing power. So an idea there would maybe to build a scalable service that I could run inside Azure containers. So I could scale these up when I needed to go build backfills for a large number of models, and then I could scale them right back down once my models were generated. On the aeronautics side, one of the ones that was interesting there was figuring out whether the clouds that you saw were clouds or contrails. And so machine learning might be a great example of sort of how I could go and process that. I could pull in a number of images of known clouds and known contrails and sort of train my model. And then people through their phones or various image devices could sort of send in a picture, and we could report back, yep, that's a cloud or that's a contrail. So image or machine learning there might be an interesting way to deal with that. On the space station one of the ones I thought was kind of fun was fashion and design, sort of about using Azure IoT services to create sort of the connected gloves or whatever. So as I move or as I do things with my fashion, they either communicate with each other. Maybe I can just wave my hand and tip my hat, I don't know. But the other would be to actually capture that data and be able to bring it up and do something interesting with that. And I'll give you a quick run through of some IoT services coming up here. Solar system. This one, Book It to the Moon, was about sort of creating educational content. We've got a great speech API that you could use to actually read your book or your multimedia off to children if you wanted to. On Earth, we've got geotagging and space aviation, and this was really be about sort of going in and dealing with storing a large amount of data and the geotag relation information around that. DocumentDB is a really cool NoSQL document database engine that we have up at Azure. Might be a great place to keep that sort of geotag data, and then maybe presenting or consuming that data with an Azure web app. And then Journey to Mars. This one really, if you looked at the challenge, was all about gaming. And so certainly, you can always go in and build games. If you looked at Azure as the tie-in there, which is Microsoft's cloud platform, and then maybe using Azure IoT services to create some sort of cool game controller. Maybe I have to lean to steer the ship or something, I don't know. Maybe that'd be a better bar game. But anyhow, hopefully the idea there is that you'll see that we have a whole family of services up in Azure: virtual machines, web applications, databases, IoT services, the list goes on, cognitive services, speech APIs, and a whole bunch of cool stuff. We have links in that ak.space apps website that I'll give you the URL to here as well, that takes you off to training materials on all of that stuff. But we were talking, or Ajay was talking about the Edison boards that they're going to make available to you. And we have some great partnerships with Intel around their Edison boards and our IoT services on the back end. So in fact, last week at our big developer conference, or the week before last, we announced these new Azure IoT starter kits, and they're specifically ones using the Intel Edison and the Grove sensor kits that Ajay is going to make available to you. And so you can actually jump up to a web app or website, and I'll show you that here in a second. But basically the idea here is I've got my Edison sitting on our Arduino breakout board with the Grove sensor, and then there's temperature sensors, there's LEDs, there's buzzers and buttons and a whole bunch of other cool things that you can use to build your projects. From there, we can actually run a Node.js application that's able to take messages about sensors or whatever the heck it is we want and send those up into an Azure IoT hub. And an Azure IoT hub is really just this message ingestion point. It's a service that we have built in the cloud that supports secure, bidirectional communication with each device. So even if you had 1 million Edisons out there in the field collecting sensor data, we can allow you to securely communicate with each one of those Edisons individually. And bidirectionally, it can send messages into the cloud, but you can also send command and control messages back down to that Edison, which is really cool, right? But once we have those messages up into Azure, you can do a number of things with them. One of the services we talk a lot about is one called Stream Analytics. And Stream Analytics is a tool that you have for, I always think of it as sort of like a ladle that you can dip into the stream of messages that's coming through. So it's a way to do sort of temporal analysis on the data that's streaming through your IoT hubs. And you could use that to maybe build aggregates. I could watch a bunch of, let's say, temperature messages that are coming in and average those over time. Or I might use that just to store and forward. Let's grab those messages and send them off somewhere else. Or maybe even do alerting. You were talking about listening to the firewall or looking for cyber security attacks. What if I want to know, if my house is overheating because too many of the room sensor data are reporting high values. And so Stream Analytics gives me a way to do that. So in the walkthrough that we make available to you, we show you, first of all, how to just grab that data and send it off to table storage, which is just a key value store that we have up in Azure. But that could be a relational database, it could be a NoSQL database, whatever. The other thing we do with it is allow you to look at those values, see if the temperatures are over some threshold, say 25 degrees Celsius, and if they are, send those off to yet another service that we have called Event Hubs. And Event Hubs are just another messaging pipeline that we have, but is more about sort of unidirectional, sending messages up, not bidirectional, like IoT hubs are. But I could send my alert messages off into into my Event Hub, and then I could use something like a web application to get both long-term sensor data from table storage. Here's all the sensor data. So, oh, there's an alert. Look, over here in Event Hub, we see an alert coming back, right? And then lastly, I mentioned with IoT hubs, we get bidirectional communication. So I could also, for example, build buttons into my web application to allow you to send commands back down. So let's say if it's temperature related, maybe I have commands that come back down to tell this to turn the fan on. It's getting hot, turn the fan on. Or okay, we're back down to a normal temp, turn the fan back off. So we actually have this as a sample that you can use based on the Intel Edisons and those growth sensor kits that Ajay is going to make available to you. So I want to jump over and just show you that to you here really quick. I actually have it working here. Although right now in Pasadena, this sensor thinks it's about negative 62 degrees Celsius, so you might want to put your jackets on. But with that said, let me jump back over here. And so first of all, this is our AK.MS Space Apps resource page I mentioned. So we've got links off to a number of resources on getting started with computer vision and virtual machines and databases and a whole bunch of other cool stuff. And then I mentioned that we announced these Azure starter kits. And in fact, here's the Intel Edison kit, and this is based on the same hardware that Ajay is making available to you if you choose to do so. And you can just follow the Get Started link, and there's documentation that sort of walks you through building that solution that I just described, step by step as you go through that. But so I've already done that, and back over here, we see some of these key components. I have my Azure IoT Hub. This is going to be where I'm sending messages into from my Edison. I have a Stream Analytics job that's basically going to go in and listen to messages coming in from my IoT hubs and those temperature sensors running on the Edison, and it's going to send them out to both an Event Hub as well as off to table storage. And it's going to do that using this query. And so the query is kind of cool here. If I look inside, I can see I actually running two queries. So the temp sensors are those temperature message data coming in from this temp sensor that's hooked up to my Edison, being shipped up over Wi-Fi into the internet into my IoT hubs. This is my temp sensor source. And we're going to go look for that. We're going to retrieve back the ID of the Edison that it was coming from. When you provision that, you actually give each of your devices their own IDs. And we'll capture the time that it happened at and what the actual temperature was. And then we're just going to forward that off to table storage. That's long-term storage. I can keep hold of that for days or weeks or months or years if I wanted to for reporting purposes. The second query is going to return the exact same data, but it's going to send that data off to my Event Hub, but only if the temperature is greater than negative 55 degrees Celsius. Remember I said I'm getting some weird readings right now and thinks it's really cold. So normally that would be about 25 degrees Celsius, but I did a quick demo fix, and we're at negative 55 here today. But anyhow, so that's what happens there. And so now I've got basically my Edison running over here. Sorry, I didn't mean to launch Studio. But so I'm actually SSH'd into the Edison, right? So the Edison's running basically a Yocto Linux distribution. So I can SSH into it, log in as root. I can run Node, I can do C++, other app, or Python, other cool stuff like that, right here on that platform. And so I've got a Node.js application here, and you can actually see it on the Edison there. And so it's actually this, sorry, didn't mean to open that up. But this command center.js is this Node.js application that's going to go off, read the sensor values off this Grove board, connect up to my IoT hub, and send the data off into Azure for me. So let me go ahead and run that. So I'm actually SSH, and I'm actually starting that program right here on the Edison. You see it's connected up to my Azure IoT hub. And it's now sending messages, right? So here's my device ID. There's that unfortunately cold negative 62 degrees Celsius that it's reporting back for some reason right now. And I called it, this is my device ID, the Intel Edison Brett Samuel Stathem's device, right? So that's just what I called it. That's my device ID. But here it is off generating messages. And so remember I said that that's going to go off to table storage. And so part of the other solution that you get is a Node.js web application. So that guy's running over here. I'm going to go launch this Node.js app. And this could be, of course, running as an Azure web app if you wanted to access it publicly. But let me go copy the URL for that. I'll pull it up in the browser, paste in the URL. And so this is the actual web application. And here I can see it's actually retrieving sensor values. So April 12th, 7:47 p.m. So these are current sensor values that are actually going from the Edison up to the IoT hub, through Stream Analytics, into table storage, and then back down to the web application. So all that stuff has just sort of happened on the back end there. Right now for the sensor, or for the alerts, notice right now I don't see any alerts. So let me come back over here, and again, we're getting about -62. I need to raise it up. Remember, my threshold was -55. So I'm going to do that simply by holding on to my sensor here, and you can read the, sorry, escape out the, gotta click away. Come on. There we go. Try that again. There we go, -24, right? So definitely holding on to it there did modify that value. And that should have now been -2 seconds. So I have an engineering issue, right? Okay. But anyhow, I did see the -24 fly through there. And so that should have gone through Stream Analytics up to my Event Hub, and that should show up under alerts. So if I refresh, sure enough, there's my -24 temperature alert popping up, right? Now in my case, I'm just displaying it, but this is just a Node.js application. So if you're a Node developer, now all of a sudden you just got a JSON message back from a service that says, hey, there's a problem. What do you want to do? Right? So you can now programmatically turn around and start to act with that. Now, one of the other things you see is that I've got some buttons up there to do some command and control. So to simulate the fan, I've got this LED connected up here, but this could be a relay, it could be a motor, it could be just about anything else you wanted it to be in terms of some kind of an actuator. And so what I'm going to do is just tell it, hey, let's go turn the fan on, it's getting hot. Oops, I missed my button. Hard to do it with 2 hands there. There we go. Woo, the fan's blowing, that's amazing! And then I can, of course, turn it back off. There we go. Cool? So those are, the cool thing about that is that that's a secure message going back down. Nobody else gets to intercept that. Only my Edison knows how to basically securely connect and retrieve those messages back. Cool? All right, so that's sort of the full cycle walkthrough through that. All that source code and instructions are all available for you up on our Azure IoT Starter Kit site there. I mentioned also, and we'll link off there from our Space Apps Challenge, but if you're looking at using Azure services, especially if you're going to be grabbing an Intel Edison board and some of those sensors back there, we've got some Azure passes that you can use to get some free Azure resources during the hack. So follow up with us. I'm here, my teammates, Daniel here, Shayna's here, Yesenia's here. We'll be hanging around for a few minutes afterwards here as well. Grab us and we'll get you an Azure pass that you can use to get free Azure resources during the Space Apps Challenge hackathon there. And then lastly, I mentioned again that URL, aka.ms/spaceapps. That's where you can learn about all this good stuff, and we'll send you off to tutorials and things like that to get you started. And if you have any questions, or if you're going to be attending a Space Apps Challenge or hosting one and you want to know more about getting Azure passes, you can send us an email at spaceapps@microsoft.com. With that, thank you.
So with both of these, I know I kind of touched on this a few times at the last meetup as well, but take advantage of these resources, right? So if you haven't worked with these boards before, if you haven't worked with Azure before, this is a great opportunity to do it. One, because you'll have a little assignment to do, your project, come up with a solution, but 2, you've got access to these people and their tools and their products in a way that doesn't come around often. So definitely take advantage of it. Use this as an opportunity to kind of take a flyer and do something different, step out of your comfort zone, and learn something new. So I wanted to talk real quick, and I'll wrap up because we want to be able to take a look at the facilities here. But I did want to touch on a couple of quick things. Working? All right. Okay, so in addition to the Space Apps Challenge, which is Friday and Saturday, April 23rd and 24th, we're also hosting a Women in Data boot camp. That's part of the Space Apps Challenge all up. Being the main stage city means that we are hosting kind of the main boot camp for Women in Data this year. As part of this, we have a really fantastic day set up. We've got speakers, we've got lightning talks that are going on. We'll have interactive stations for people to interact directly with presenters and their tools and their projects and their ideas. Really targeted at women and girls who are interested in tech, who are involved in tech, but want to kind of learn more and get more involved. It's not so much about the experience level as it is just getting people involved so we can broaden the diversity of people who are involved in tech. There are a lot of ways to get into tech now. There are a lot of things to do once you're in tech. As you see from Ajay, going forward, there's going to be even more. Everything is going to be based in tech. So this is really a great day. It starts at 8:30 in the morning with sign up. We'll run till 4:30 that afternoon. It's a great day to come, get involved, immerse yourself in tech, hear from some fantastic women. We got 3 from NASA here. Renee Wynn, Deborah Diaz, and Beth Beck. These are all the women who put on Space Apps Challenge globally. Kimberly Bryan, Black Girls Code, a really great group here. Astronaut Doug Wheelock, I think he's the only non-female on the list here. But he's awesome. Wheels, great astronaut, great speaker, and he'll be involved throughout the day. The list here, I mean, they're awesome collection of people. Very strong day, so I definitely encourage you to come. It's free. Register. Space is somewhat limited, so like tonight, if you want to go, please go. Yes.
What's the maximum quantity for people? Since that space is limited.
Space is we're looking for about 100 people.
Okay.
There's room,
sure.
But it will fill up.
Yes.
So get in now. So basically, just I can't tout this event enough. It's going to just be an awesome day, and I encourage you all to come, especially in the women. If you'd like to sign up, here is the URL. I know it's a bit long, but you can go to 2016spaceupchallenge.org, search for Pasadena, and then up top you'll see that there are two links to register, 2 buttons, one for the main Space App Challenge and one for the boot camp. And the boot camp is the Women in Data boot camp. And then real quick, because I know it's a big part of the weekend and it's a part that doesn't necessarily get a lot of attention going in, is there is judging at the Space Apps Challenge. While it's a collaborative event and it's open data and it's open source, there are some great opportunities to get some recognition for your solutions. So I just wanted to hit on this real quick, and then we'll get on to the tour. The judging works kind of at a granular level, and then it expands from there. So on a small level, we start with local judging and local prizes for the Pasadena event. So the weekend of Space Apps will do their challenges, create their solutions, and then on Sunday, you will present your solution. We'll probably have 5 minutes, maybe 10 minutes per team to present your solution to the audience, which will be all the other participants, as well as the judges panel. Have great judges on the panel this year from NASA, Microsoft, Intel, Socrata, Off Campus, Starburst, and we'll probably add a few more as well. From all of your solutions at Space Apps, we will choose a few awards. We will choose a first place, we will choose a second place, and then you guys will choose a People's Choice Award. And I put hashtag, it kind of got cut off, start your hashtag now, because it will be voted on. The People's Choice Award winner out of Pasadena will enter a global challenge, and the winner will be the one who gets the most, makes the most noise on social media. So if you have a project and a team now, it doesn't hurt to get started. So come up with a hashtag, get a Twitter page going for your team, and just start rolling it out. The judging criteria will be, my list away, is broken down into 6 categories. And this is how NASA will be reviewing the categories, or these solutions, and it's what we will do at a local level as well. So, best use of data, solution that makes the best, makes space data accessible or leverages it in a unique application. Hardware, pretty self-explanatory, but most innovative use of hardware. Mission concept is the one with the most plausible solution concept and design. So something that seems like it can actually happen, turn into a product, something usable. Galactic impact will be the solution with the most potential to improve life either on Earth or out in the universe. So thinking about traveling to other planets, or taking a trip to another planet, possibly. Most inspirational is the solution that captures our heart, which it's fantastic that they've got that this year, because it really opens up a lot of cool possibilities, especially when you think of the challenges of long-distance space travel and long-duration missions and the tax that that has on us on a human level. I think there's a lot of interesting opportunity there. And then the People's Choice Award, again, is that one that will be voted on by you guys to choose our winner, and then voted on you guys as a global audience to choose the all-up winner. So that one is out of the hands of the NASA judges. In addition to that, we've got the challenges offered by our sponsors. And these tie in well with the other ones, but are a little bit different. So Microsoft is offering their challenge for the best use of Azure tools, Intel for the best use of their boards, Socrata, the best use of their APIs, and SupplyFrame is offering an award. SupplyFrame were our hosts at the first meetup. They've got Hackaday in their new design lab on Del Mar, just south of the park. And they're offering one as well based on the best use of hardware or a hardware accessory as part of the software solution. So we'll post more information on these, on what you have to do to be eligible for each one, the prizes that are available online at 2016.spaceappschallenge.org, Pasadena. But these are all great things that kind of push you on to kind of guide kind of where you're going with your solution. So definitely check these out. Try to make yourselves available to as many of these, or eligible for as many of these as possible. If you win, sorry I'm blowing through this, but I want to get on to the next part. But if you win in Pasadena, then you get elevated up to the global challenge. And we will send our first and second place teams up to the global challenge. They will get reviewed by NASA judges. And to do that, first thing you gotta do is win in Pasadena. Second thing you have to do, and you'll do this the weekend of the event, is create a project page. And you'll be reminded of that a few times during the weekend. Then you have to include a link to code in a public repository somewhere so that people can check it out. After the event, so after the weekend of the 23rd and 24th, if you're our first or second place winner, then you'll be asked to create a 30-second video about your solution. It can be turn on your webcam and just talk about it, or it can be something produced. It's up to you. But you will be asked to do that. And then keep your code that you developed during the event open source, at least through the judging period. The NASA judges will consist of NASA experts as well as challenge owners. So the people who actually wrote the challenges will be involved in reviewing them. They will choose 25 finalists. So imagine there's 200 cities, each one putting 2 judges, do the math, 400 people. They'll choose 25 out of that, 5 per category. And then from that, they'll choose 5 winners, plus the People's Choice, which will be chosen by you guys. And those winners get invited to a launch. So it's not an all expense paid vacation, it's an invitation. You have to get yourself there, but if you do, they'll get you from outside the facility to a good viewing spot, and they'll get to see it. And if you've not seen a launch, which I know is not a common thing, it's fantastic. Especially, I mean, if we're doing tests and stuff for the next 5 years, that's great. And then, but put on your bucket list sometime in your life when we start sending people back up on rockets from the U.S. Go see a launch. It'll change your life. So, but for this, we'll get a chance to see a launch, and some fantastic new tech is coming online. So the opportunity to see something very cool is there. And finally, if you haven't seen it, here's our poster for this year. If anyone attended last year, we had an awesome poster from Sid Mead. This year, the poster was designed by Tom DeLonge of Blink-182. He's a big space fan and a very good friend of mine. And so happy to get him involved. We'll probably have some sign buttons and some things around at the event. But thank you all again for coming. If any questions about the event or anything, come ask me now or hit me up online. Happy to answer and help you out in any way I can. And thank you for coming. And now we're going to take a quick tour of the facilities. And I don't know, do we still want to break up into 2 groups? Or do you want to?
It probably would be good to take one group. You wanted to do the library and the machine shop?
Yeah, so you can take half and I can take half.
Yeah.
Okay, so let's do 2 groups. I mean, kind of just split up this way. I want to split your parties up, but
it's like a live blog.
One half, this half will go. I'm on
Brandon, you messaged me online.
Yeah, I'm Scott.
Come
out this way.
Say,
Okay. We have to go kind of out anyway, so.
Okay.
We were